to record this. Okay. So equal masses of potassium and chlorine react to completion. So once again, I know that the balanced chemical equation is this: K plus 1/2 Cl2 is going to yield KCl. Let me shut this door. Oh boy. So I'm reacting equal masses of these two things. In other words, they're telling me about both reactants. So what kind of problem is it whenever they're telling me about how much I have of both reactants? It's a limiting reactant problem, isn't it? So I've got to think about which one is going to be my limiting reactant. Well, if I react equal masses of this, there are several ways to solve this question. But what I realize is that my equation out as it's balanced is 1 mole of potassium plus 1/2 a mole of Cl2. Well, 1/2 a mole of Cl2 is just like 1 Cl, 1 chlorine. So Mr. Sanford has a question. So let me go unmute him. Oh, he's waiting to be admitted. Whoops. Mr. Sanford, do you have a question, my guy? If he has a question. Mr. Sanford, if you have a question, just type it in the chat, okay? Okay, so how can I think through this whenever they're reacting with equal masses? Well, I can make that mass whatever I like. It just told me that they're equal. So why don't I make their mass just the molar mass of one of them to maybe help me think through this. So the molar mass of potassium is about 39.1 grams, and that gets me 1 mole. So I have 1 mole of potassium. The molar mass of chlorine, 1/2 of Cl2 is just 1 chlorine, is 35.45. So if I react the same mass, and the molar mass of chlorine is 35.45, I know I have more than 1 mole. I have 1 point something moles. So I have greater than 1 mole, greater than 1 mole of chlorine. So if potassium reacts with chlorine in pretty much a 1-to-1 ratio, in other words, 1 mole of potassium reacts with 1/2 of Cl2, which is just 1 Cl. In other words, I could write it like this: 1K plus 1 Cl. Of course, that's not correct chemically speaking, because we know that's Cl2, but stoichiometrically speaking, these two things are equivalent to each other. I know right away that I have more than enough chlorine if I have these two things in equal mass. So I know that chlorine, Cl, is my excess reactant. So what's going to be left over after this reaction goes to completion? Well, of course, I'm going to have made some product, and then I'm going to have some chlorine left over. So the answer to number 5 is C. Okay, that one was really hard. People have a hard time with this question every year, but you have to realize that it's asking you, it's a stoichiometry question, and it's asking you about what happens when you have equal masses of these. It's a limiting reactant problem, and you can kind of figure it out from there. Okay? Give me 1 second. Mr. JM has a question. Sorry, I'm trying to figure out how I can. Okay. Mr. JM, I'm going to unmute you and let you ask your question. Okay, Mr. JM, you are unmuted. Ask your question.
So, how would you get 1 mole of chlorine from like the 1/2 mole of chlorine gas?
Because 1/2 of Cl2, what's half of 2? It's just 1, right?
1.
So what I'm saying is that this is stoichiometrically, in terms of amounts, these are equivalent statements. In other words, this is the same thing as this if I'm trying to figure out amounts of things. Does that make sense?
Yes.
Okay.
And then could you repeat the last part of how you find the answer?
Yeah, so because it tells me that I combine equal masses of them, I can make that mass whatever I want, basically. So I just chose something that would be fast to help me figure out how many moles I have. I have to compare the molar amounts, how many moles of each one I have. So the fastest way for me to do that was just to say, oh, well, let me just say that I have the molar mass of potassium of each of them. You don't have to do that. I can show you another way of doing it, but I recognize that was going to be the fastest, easiest way for me just to say, okay, I have 1 mole of potassium, 39.1 grams. Well, if I have the same mass of chlorine, because one chlorine has a smaller molar mass, its molar mass is only 35.45, I have more than that. So I know that chlorine has to be my excess reactant. You could have picked any mass. You could have said that that maybe they both have 100 grams and you figure out how many moles you have, something like that. Really, you don't even have to think about, you don't even have to pick a specific mass. All you have to realize is that in your reaction, for every 1 mole of potassium, because the reaction is balanced this way with the 1/2 right here, because this is true, for every 1 mole of potassium, my reaction asks me to also have 1 mole of chlorine. And I know that chlorine on the periodic table has a smaller molar mass than potassium. Chlorine has a molar mass of 35.45. Potassium has a molar mass of 39.1. So because chlorine has a smaller molar mass, if they're present in the same mass, the same amount by mass, then chlorine will always have more moles because it has a smaller molar mass. In other words, if I have 100 grams of both of them, I'm going to have more moles of chlorine in there because chlorine has a smaller molar mass. So you don't even have to like think about what the mass is. You just realize that their masses are equal, but because chlorine has a smaller molar mass, it's going to have more moles. So chlorine is my excess reactant. I'm going to have some of it left over. That was a pretty hard stoichiometry problem. Okay, let us proceed. Okay, question 6 is a great one that actually relates to what we're doing in this unit. Question 6 says, which of the values of delta H for the process in the table is or are less than 0? So what's true when delta H is less than 0? That is an exothermic reaction, right? Delta H is negative. Exothermicity, I know, comes from the formation of attractive forces. Formation of attractive forces. When attractive forces form, I know that energy gets released out. So where do I have attractive forces forming? Is this process forming an attractive force? No, it's ripping apart a solid. So that's going to have a positive delta H. Is this the formation of an attractive force? No, that's ripping away an electron that was attracted to that atom. So that is going to be endothermic. Here, this is an attractive force being broken once again. 2 atoms of chlorine were bound together, and I ripped them apart by breaking that bond. Bond breaking is always endothermic. This is an attractive force being formed, right? The chlorine atom has captured an extra electron. That electron is attracted to the nucleus of the chlorine. I have formed that attractive force. That's going to be a negative delta H. And here, of course, these ions attracting to form an ionic bond will be a negative delta H as well. So the answer was B. Only Y and Z are exothermic processes. All right, question 7. It's observed that this reaction goes essentially to completion. Which of the following is a true statement about the thermodynamic favorability of the reaction? Well, first of all, it tells us the reaction happens. So we know the reaction is favorable. So A and C have to be the correct, have to be our options. In other words, we can get rid of B and D because those are crappy. And then we remember that, in order for something to be favorable, the delta G has to be negative. So now I'm thinking about, well, what is really responsible for making that delta G negative? And if we go back up to the very top, it said that the whole reaction had a delta H that was negative 400 something. I don't remember quite what it was. that delta H was around negative 400. That's incredibly exothermic. So I know that it's driven mainly by exothermicity. And this process, the whole reaction is solid potassium plus gaseous chlorine forming KCl, which is a solid. So what's happening to the entropy of my system? Well, the entropy is decreasing, right? Because I have a chaotic gas and now I trap it in a crystalline solid. So my disorder is decreasing. So I know that my delta S is negative. That is not going to help me get a negative delta G. In other words, my entropy of my system is doing the opposite of what nature would want. So it is not a favorable process due to entropy. It is a favorable process due to the exothermic enthalpy. So the answer A is the best answer. What's up, Henry?
Is it past 9? Or is it past 10 o'clock?
Yeah, you have 5 minutes until it's 10 o'clock. Okay? All right, so question 7 should have made some good sense. Question 8 is a Hess's law question. So I want to find what expression is equal to taking 2 moles of, taking 1 Cl2, adding 2 electrons to it, and getting 2 ionized chlorine atoms. So you can see here that I'm going to have to do several things. I'm going to have to find the process that breaks chlorine apart, and I'm going to have to find a process that takes 2 atoms of chlorine and adds 2 electrons to ionize them. So those are the 2 processes that I want. And I need to look back up at the table and see what 2 processes I can add together through Hess's law to get those 2 processes. So I go back up to the table, and let's see, I can see that process X is ripping apart my chlorine, right? So, and that's in the direction I want. And process Y is chlorine capturing an electron, right? But it looks to me like I need that to happen twice, because this is only for 1 chlorine atom and I need to ionize both of my chlorine atoms. So I believe the answer is going to be X plus 2Y. In other words, I need to do process X. I need to rip apart the chlorine to get just chlorine atoms, 2 chlorine atoms. And then I need to multiply this whole thing by 2 and add those together to get the overall process that I want. So the answer, X plus 2Y, is C. 8 is C. Okay? All right. Oh boy. Okay. All right. I'm assuming no one has any questions, so we're just going to keep on going. Question 9. This looks like it's going to be a Hess's law question. Here's the picture on the puzzle box. Here are my puzzle pieces. I'm trying to rearrange these to get this. So I'm trying to find Fe2O3 as a solid reactant. It's right here, and I need 3 of them. So I need to go through and multiply everything here by 3. Uh, 28 times 3 is something. 84. So this becomes a negative 84. This puzzle piece does. And then let's see what else I need. I need Fe3O4 as a product, but it's right here as a reactant. And I need 2 of them. So I'm going to cross this whole thing out. And I'm going to multiply it by -2, basically. I'm going to flip it and multiply it by 2. So I'm going to get 6 Fe solid plus 8 CO2 gas as my reactants. I've taken the products, put them as reactants, multiplied by 2. And that's going to yield 2 Fe3O4 solid and 8 CO gas. My new delta H is then going to become positive 25, because it was negative 12.5 and I flipped it and multiplied it by 2. So I flipped the sign and multiplied the delta H by 2. So now I need to confirm that this does indeed get me the reaction I want. I have 3 Fe2O3 there. I have 9 CO as a reactant and 8 CO as a product. So those are going to cancel, and that's going to cancel, and I will get a single CO left over because I had 9 as a reactant and 8 as a product. It looks like then I have 6 irons as a product from this reaction, 6 irons as a reactant from this reaction, so those will perfectly cancel. I have 9 CO2 as a product, 8 CO2 as a reactant, so 8 of those will cancel to get me CO2 as a product. And then I have my 2 Fe3O4 as a product right there, and that gives me the perfect reaction that I wanted. So I now know that by adding these 2 steps, I get my overall reaction. I need to add negative 84 plus 25, and that will of course get me negative 59. So that is the answer. All right. Okay. Question 10. I want to calculate the delta H of the reaction, and it looks like I've been given all these heats of formation. So remember that the equation is that the delta H for the reaction is the heats of formation of the products minus the heats of formation of the reactants. So I need to add together the heats of formation of the products. Where my products are IF5, so that's negative 840, and 2IF, so plus 2 times negative 95. That will give me the total heat of formation of the products. I need to subtract away from that the heats of formation of the reactants. I have 1 IF7, so negative 941. And then remember that the heat of formation of I2, which is not even on the list, that's an element in its standard state, and it has a heat of formation of 0. So I'm just going to add 0 to that. And you're just going to perform this mathematical operation. And whenever you do that, you get letter D, negative 89. Just like that. Okay. And now question 11. If the combustion of solid aluminum form aluminum oxide, which has this delta H, performed in a calorimeter, which of the following statements will be true? The reaction is exothermic. So the reaction is indeed exothermic. So C and D are crappy answers. I can get rid of those right away. Notice that this is always a multiple choice strategy that we want to use to try to eliminate bad answers. What's up, buddy?
Is it past the time?
It is. It's 10 o'clock. So you need to go work on your math now, okay?
Well, there wasn't 10:00.
Well, that means it's past 10. Yeah. So you have a worksheet and you have iReady to go work on, okay? Okay, dude.
But you need to help me get on iReady.
iReady is already on the computer. You just need to click over. Do your worksheet first and I can help you, okay? The answer is A, because letter B, the system does not absorb heat from the surroundings. That's the exact opposite of what happens. The surroundings absorb heat from the system because the system is releasing heat out. Okay, question 12. This is just a calorimetry question. Oh boy. Ugh. Okay. Oh, and this was the one that we had a typo on. So this should say joules. So this reaction is performed in a calorimeter, and I formed 23 grams of HCl. So first thing I need to notice is that this amount of energy, the delta H being negative 336 joules for this process, that is tied to me forming 3 moles of HCl. But I am forming 23 grams of HCl. So this is not the actual amount of heat energy released. I need to figure out how much heat energy is released. Negative 336 joules are released for every 3 moles of HCl. And I know that in 1 mole of HCl, the molar mass of that is 36.46 grams. And I know that I'm only using 23 grams. So I would need to perform this calculation. And when I do that, I get 70,653 joules. Is that right? No, that's not right. 70.653 joules must be, sorry, let me calculate this real quick. Yes, 70.653 joules of energy. Negative. So that's the delta H for this reaction when 23 grams of HCl are formed. Don't forget that these values they give you are always going to be tied to a reaction, kilojoules per mole or joules for a certain reaction, joules per 3 moles. And I'm not using 3 moles. I am only using 23 grams. So I've got to figure out, do a quick table ladder to figure out how much energy I actually get. So the reaction releases that much energy. That means my calorimeter, my water in the calorimeter absorbs that much energy. So I can say that the energy absorbed by my water is this value, and that's going to equal MC delta T. And I know the mass of the water is 100, specific heat capacity. I can solve for the delta T, which is what I'm being asked. By how many degrees Celsius does the water change? Of course, it's not going to be negative. I can eliminate those answers right away. My reaction system is exothermic, but that energy flows to the water to increase the water's temperature. So remember that the delta H for my system is equal to the negative delta H for my surroundings. My system is experiencing a negative delta H, so my surroundings would be experiencing the opposite of that, positive delta H, so positive 70. Anyway, you end up getting an answer of D whenever you do that math to solve for delta T. Oh boy, okay. Are we doing okay? You guys are not, oh my. You guys are not talking much, so I'm assuming that you're with me. Okay. Question 13. What is the enthalpy change for the sublimation of iodine represented below? Sublimation means solid to gas, right? So it looks like this is going to be a Hess's law question. This is the picture on the puzzle box for which I'm trying to find the delta H. And these are the 2 steps. So I need to get solid as a reactant. It's a reactant here, and I need a 1 whole mole of it. I only have half a mole, so I need to multiply all these by 2. That's going to become a 1. That's going to become a 1. I'm going to get 2 of these, multiply this by 2 to get 52. And I need 1 mole of gaseous I2 as a product. It's present as a reactant here, so I need to flip this whole thing and multiply it by 2 because I only have half a mole right now. So when I flip the whole thing and multiply it by 2, I get 2HI is going to yield I2 plus H2, and the delta H of that is going to be 10 kilojoules per mole. So I add those up, I get an overall delta H of 62. Someone was kicked out of the chat. Oh boy. Okay, let me try. Whoops. If you guys have any issues with the chat or with viewing this right now, I am recording this, so you guys will be able to go back later if you have questions. All right, hi, Ms. Cashman. I'm assuming you're back in, hopefully. Okay. So 13 was just a Hess's law question. Multiply the top reaction by 2, multiply the bottom one by 2, and flip it. And you'll get letter E once you add those together. Okay, questions 14 and 15. Isn't everyone just having so much fun? Okay, 14. What's the standard enthalpy of formation of NH3? So they've given me the heat of the enthalpy of reaction for that whole reaction. How can I get the enthalpy of formation? Well, I know that delta H is equal to the heats of formation of the products minus the heats of formation of the reactants. So the heats of formation of my products, those two products are elements in their standard state. That's how they're typically found. So those are 0. So I can say this. I can say that 92 equals 0 minus the heat of formation of my reactant NH3. And I have 2 NH3s right now, so I would multiply that by 2. So I end up getting this algebraic equation. 92 equals negative 2x, basically, where x is that heat of formation of NH3 that I'm trying to find. That was just you starting with this equation. The overall enthalpy change is equal to the heats of formation of products minus heats of formation of reactants. We know the heats of formation of the products here are 0. And so this is the equation that you end up with. So just perform that algebraic equation and you get an X of negative 46 kilojoules per mole. So 14 is B. Okay. Number 15. Here we have 1 gram of cashew burned in a calorimeter containing 1,000 grams of water, and the temperature of the water changed this much. In another experiment, 3 grams of a marshmallow were burned containing 2,000 grams of water, and the temperature changed this much. Based on this, which of the following can be concluded about the energy content for just 1 gram of each of the substances?
Daddy, I finished all my math worksheets.
Awesome, dude. Why don't you practice writing your numbers?
This and this.
So on the back of that one, why don't you go practice writing some numbers, okay? Yeah, how about numbers 1 through 10?
Why?
Because you need to practice. Okay, then I'll come help you with iWriting, all right?
Can I do them in here?
If you want to, sure. Okay, so I'm trying to figure out, I want to make a ratio right now of how much heat energy 1 gram of each of the substances could release. So what I could do is write a little equation to figure out the heat energy actually released in these 2 experiments. So for the cashew, I know that delta H is MC delta T. The mass of my water was 1,000. The specific heat of my water is 4.2, and the delta T was 5.
Daddy, is that one?
That's great, buddy. So you do that real quick, and you get a delta H for the cashew of.
Daddy, 2? Is that 2 right? Daddy, is that 2 right?
It is, buddy. Of 20.9 kilojoules, and that's for 1 gram of a cashew being burned. So if I divide that by 1 gram, I'll get kilojoules per gram. If I repeat that for the marshmallow, I can see that the marshmallow would have a delta H equals MC delta T. This time I used 2,000 grams of water, 4.2. I got the same temperature change of 5 degrees, 25 to 30. And you do that, and you get
Daddy, I still want to erase that 2 and start over.
okay, bud. Hey, I'm working right now. But that's per 3 grams. We want to figure out what it is for 1 gram. So you divide that out, and you get a 13 point something kilojoules per 1 gram of marshmallow. So it looks like the cashew releases more energy. Releases more energy per gram. Okay. Now there's a simpler way of figuring this out, and this is that that in the marshmallow I have 3 times the mass of the marshmallow than the cashew, but it was only able to heat up 2 times the amount of water by the same temperature change. So the marshmallow has to release less energy per gram than the cashew does, because I would expect that 3 times the marshmallow heating up twice the amount of water to have a greater temperature change if the marshmallow was able to release more energy per gram. So you can do it mathematically, or you can think about it conceptually like that.
I can't. How do you draw a 5?
1 second, buddy. Y'all give me 1 quick second. Okay. All right. So 16, molecular solid coexists with its liquid phase at melting point. The liquid solid mixture is heated, but the temperature does not change while the solid is melting. So in other words, we have something exactly at its melting point. So we should be thinking about these heating and cooling curves that you guys are hopefully familiar with. So remember that this is a solid, this is a liquid. On the x-axis is how much heat energy I'm adding. On the y-axis is temperature. So I'm right here. I'm at the melting point, adding heat energy, but the temperature is not increasing. I hope you remember our discussion about that, about why we said that's true, because all of the energy, all the heat absorbed by the mixture is used in overcoming intermolecular attractions. This is a molecular solid, like ice is a molecular solid. So what's holding the particles of the solid together? Those attractive forces would be intermolecular forces. All the energy I'm adding now to melt the thing is going to weaken and loosen those intermolecular forces. So the answer to 16 has got to be B. All the energy is used in overcoming those intermolecular attractions in the solid. Okay. 17 and 18.
I tracked this 1 through 10.
That's great, buddy. Why don't you do it a couple more times? All right. So the reaction between SO2 and O2 by that equation above, I have this table that gives me the entropies of these values. Which one is going to help me calculate the entropy of SO2? So I know the entropy change for the whole reaction. And remember that I have an equation for that. Delta S for the reaction is going to equal the entropies of all the products minus entropies of all the reactants. Quite simple. I want to figure out what the entropy change of SO2 is. So I'm going to write this equation. I know that this is equal to negative 187, and that's going to equal 2 times my product of SO3, so 2 times 257. That would be my products, minus all the entropies of my reactants added together. That's going to be 2 times X. That X is what I'm trying to find, plus whatever the entropy of my oxygen is, 205. All I have to do is rearrange this equation and solve for X. When you do that, the algebra, when I solve for X, gets me an answer of C. C is going to be the correct equation. Okay, question 18. What can be concluded regarding the strength of CH, NH, and OH bonds in the molecules shown above? Well, what I can do is I can recognize that I'm given the enthalpy change of the overall reaction for each of these processes. And each process requires that I break carbon-hydrogen bonds, break nitrogen-hydrogen bonds, break oxygen-hydrogen bonds here, and then I form carbon-hydrogen, nitrogen-hydrogen, oxygen-hydrogen. And then I'm also forming hydrogen-chlorine bonds. So remember that in terms of bond strength, these delta H's, the delta H for the reaction, is going to be equal to energy in to break reactant bonds, plus energy out, which is a minus, to form product bonds. So you can see that each time I am, for example, in this reaction, I am breaking 4 carbon-hydrogen bonds, and I am forming 3 carbon-hydrogen bonds. This time I'm breaking 3 nitrogen-hydrogen and only forming 2. This time I'm breaking 2 oxygen, hydrogen, only forming 1. So each time I am forming 1 less, and I'm also forming HCl every time. So this is going to allow me then to just directly compare these values. And right away I can conclude that the oxygen hydrogen must be the strongest, because this reaction is the only one that is overall endothermic. And because I am overall breaking 1 oxygen hydrogen bond, then this can give me some information about how strong that bond must be. So I know that the oxygen hydrogen bond is the strongest, because here in this reaction where I'm putting energy in to break just one of those, that requires the most the largest amount of energy to be put into the system, just like that. So 18 is C.
C.
Yes.
C.
All right. So number 19. Here's the idea behind number 19. You had to read this question. Read this question carefully. Oh my gosh. Okay. I don't know why that's highlighted, but we're just going to deal with it. So good job, buddy. That looks awesome. Why don't you go take a break and I'll help you with your math later. So a chemistry teacher is mixing two different solid powders in a beaker. So there's a chemical reaction going on between these 2 different solids. The teacher then places that beaker. So I have 2 different solids in here, maybe solid X and solid Y, and they're reacting in the beaker. And then I put the beaker near some water. And as time goes on, that water ends up freezing. The bottom of the beaker is frozen to the wooden surface. So I know that there's a chemical change going on because these solids in the beaker are reacting with each other. And I know they must be sucking heat energy in from the water, because I know that the water is spitting heat energy out because it's decreasing in temperature so much that it's freezing. And it's forming those strong attractive forces between its molecules. So therefore, its delta H is negative. So the delta H of the system here, my reaction must be positive. It has to be an endothermic chemical change that's happening, because the beaker and the water, they're giving off heat energy into the endothermic process in my beaker. All right, so 19 was D. Oh, nice, dude. That's awesome. All right, and I think this is our last multiple choice question before the free responses. So based on the bond energy shown to the right, which of the following diagrams best represents the change in energy as the reaction represented below occurs? Thank you, James. Okay. So what I can do is actually figure out the delta H for this process, because the delta H, the overall energy change, shows up in these graphs right here, for example. This would represent a negative delta H of 190. How do I find the delta H when I'm given bond energies? Remember, it's bonds broken minus bonds formed. So my delta H is going to be, looks like I'm breaking a 430, breaking an HH, I'm breaking a ClCl, and then subtract away from that the energy that comes out when you form new bonds. It looks like I am forming 2 HCl bonds. So 2 times 430. That's going to tell me the overall energy change of this chemical reaction. And let's see what we get when we do that. 430 plus 240 minus 430 times 2. We get negative 190. So I now know that the overall energy change of this process, the overall delta H of the reaction, is negative 190. So I need to find a graph that shows that from the reactant side to the product side, the amount of energy goes down 190 after I've overcome that activation energy. And the answer is A. A is the only graph that does that. All right. So my reaction is exothermic, A is exothermic because my products end up at a lower energy than my reactant started with, okay? Okay, guys, why don't you take about 5 minutes of a little break. I gotta go get my kiddo started on his little math program on his computer. So I will be right back. Okay, we good to go? All right, let's do some FRQs. Thank you guys for being patient with me. I know this is kind of a mess, but hopefully this is useful, beneficial. How are we doing on the exam? Someone give me a thumbs up or type something in the chat. I don't know. Tell me how you're doing. Anybody? Nobody? Failing. Boo. Mr. Hayes says pretty good. Sad face. Don't give me a sad face. Okay, this test, I'm going to give you guys quite the large curve on it because, you know, we're not able to do a group retake and stuff like that. So don't worry too much about your grade. You guys will be fine. Okay, let us proceed with the free response question. So, no judgments, Ms. Stark. We're all trying to get used to this system. Okay. Let me zoom out a little bit on this. Okay. So, okay, I want to calculate the standard entropy change for the reaction. That's super easy. I know the entropy change is entropy of products minus entropy of reactants. So I need to take the entropy of my products, which are these guys right here, add them together, and then subtract away this one because that's my reactant. So I'm not going to take the time to do that math. You guys can do it, but you should have gotten an answer of positive 127.2. You must have units, joules per mole Kelvin. We need to pause and see if that makes sense. Does it make sense that I got a positive delta S, a positive entropy change? It does, because I went from 1 mole of a gas to 2 moles of a gas. So of course my disorder increased. So that's correct. Using the data in the table below, calculate the standard enthalpy change for this reaction. So for part B, how can I find enthalpy change based on bond energies? Well, I know that I'm going to go through, and for every bond that I break, I'm going to treat that as a positive value. For every bond that I form, I'm going to treat that as a negative value. So I can construct an equation for part B. It looks like I'm going to be breaking 1, 2, 3, 4, 5 CH bonds. So 5 times 4, 13. I'm going to be breaking a single carbon-carbon bond, 348. I'm going to be breaking a single carbon-nitrogen bond, 293. And I'm going to be breaking 2 nitrogen-hydrogen bonds, 391. You do that calculation, and that will be the energy in to break all these bonds. And then you have to subtract away from that. I'm running out of space. Subtract away from that the energy that comes out whenever you form all of these bonds. So it looks like I'm forming a single carbon double bond, 614. I'm forming 1, 2, 3, 4 carbon hydrogen bonds, 413. And then I am also forming 1, 2, 3 nitrogen hydrogen bonds, 391. So all of this added together minus all of this added together, energy in to break old bonds minus energy out when new bonds form. You do that, and the answer that you get is looks like I'm getting positive 49 kilojoules per mole. Let me double check my math on that, but I believe that is correct. Yes, positive 49 kilojoules per mole. Okay, so based on our answer to part B, predict whether the temperature of the contents of the container will increase, decrease, or remain about the same. What have I just found in part B? I have found the delta H for the system. What are they asking me about? The contents of the insulated container. That's the surroundings, isn't it? So delta H of the system is negative delta H of the surroundings. If my system is sucking energy in, my surroundings have to be losing energy. So part C, the temperature is going to decrease. The temperature has got to decrease because I'm being asked about the surroundings. The contents of the insulated container, that is the surroundings of this chemical reaction, whether air or water or however we're doing this reaction. So because my reaction itself has a positive delta H, my surroundings will have a negative delta H. They'll be losing energy, so their temperature should be decreasing. Part D, is the process favorable at 298? Justify your answer. To do that, I have to figure out a delta G. Delta G equals delta H minus T delta S. I found delta H, I found delta S, so I can just plug and chug with 298 right here. So 49 minus 298, I have got to be careful with my units. This is in joules. My delta H here in part B, the 49 is in kilojoules. So I need to convert this value to kilojoules. That is a positive 0.1272. Please watch your units. Entropy is typically always in joules. Enthalpy is typically in kilojoules. Whenever you do your delta G equation, you have to make sure that those are matching and agreeing with each other. Whenever you do that, you end up with a positive value for delta G. So your answer for part B is no, because delta G is greater than 0. Delta G is positive. It is not a negative free energy change. So therefore, it's not favorable at this 298 Kelvin temperature. All right, that was free response question number 1. Hopefully not too bad. Miss Young has raised her hand. Miss Young, let me find you real quick and unmute you. Okay, Miss Young, you have been unmuted. What's your question?
So I was looking at it. Isn't the equation products minus reactants?
For part B, is that what you're asking about?
Yes.
It is not. So this is the thing that I really emphasize that you guys not get mixed up. It's products minus reactants if we are dealing with heats of formation of products minus heats of formation of reactants. But that's not the information I've been given. I've been given bond enthalpies. Whenever you're looking at bonds, the delta H is going to be equal to energy in to break the reactant bonds. That has to be a positive value because the energy has to go in to break those bonds. And then you get energy out minus all the product bonds that are being formed. So these two equations are kind of opposite of each other. Heats of formation will be products minus reactants. Bond enthalpies, though, will be reactants minus products. Does that make sense?
Mm-hmm.
Okay, excellent. Very good question. All right. Oh, yes, Miss Young.
So you said that if you get like a wrong answer, but you continue with it, you can still possibly get points. I got
Uh,
a next.
yes, correct. So, like in part B, if you used it incorrectly, you'll get part B wrong. But if you got a number and you use that number correctly, even though it's a wrong number in part C and D, you can still get some partial credit for those. Yes, that's correct. All right. Yay, let's go on to question 2. We are almost done. All right. So it's telling me that the standard state of bromine is liquid, but the standard state of iodine is solid. The enthalpy change for liquid to gas, solid to gas is given in the table above. So why is the enthalpy change for iodine larger than for that of bromine? Include a brief discussion of particle interactions. So you had two main things you could have said in part A here. First, you could have said that iodine is changing all the way from a solid, oh boy, sorry, please hold. Okay, why is it still highlighted? Okay, iodine is changing all the way from a solid to a gas. So of course that's going to require more energy just to break apart those intermolecular forces. In other words, the intermolecular forces for iodine are much more effective, much more efficient. They're stronger because they're holding together the iodine I2 particles as a solid. So if I were to draw a picture of this, here's a bunch of I2 molecules. And whenever I have iodine as a molecular solid, remember what's happening whenever I go from a solid to a liquid or a liquid to a gas or whatever. I am breaking these intermolecular forces, so these are getting broken. However, for iodine, those were really strong because they were successfully holding the particles together in a solid crystal. So to break those, of course, it's going to take more energy than it does just to vaporize the liquid bromine, because bromine is a liquid at this temperature. It does not have as strong or effective intermolecular forces. You could have also said that iodine is a larger molecule than bromine is, so therefore it has stronger London dispersion forces. You didn't necessarily have to get into that much detail, but you did have to say that iodine is using stronger, more effective intermolecular forces because it is a solid, and therefore, of course, it's going to take more energy to break those apart. For part B, which process has a greater change in entropy? They both are going to have a positive delta S because the entropy is increasing. I'm going from a liquid to gas, solid to gas. Which one is going to have a greater positive delta S? Of course, it is going to be iodine sublimating, this process here, because I'm going from a very orderly solid to a very chaotic disorderly gas. That's a bigger change in entropy than going from just a liquid to a gas. So you had to say the iodine sublimating process, iodine going from solid to gas, and you had to give some explanation. Okay, assume the entropy change for the vaporization of bromine is 93.1. What's the boiling point of bromine? So hopefully you remember how to do this. You have to figure out at what temperature does this process just become favorable? In other words, at what temperature is delta G crossing from a positive to a negative value? At what temperature is delta G 0? So you set delta G equal to 0, rearrange this equation and solve for temperature. You're going to get delta H equals T delta S. And then solve for temperature, you get temperature equals delta H divided by delta S, just like that. We need to be careful with our units because once again, delta H is in kilojoules, this delta S is in joules. So my delta H is 30.91. My delta S, to go from joules to kilojoules, I have to divide by 1,000, 0.0931, and that will give me the temperature. And I believe that you're going to get something close to 332 Kelvin for your answer. All right. Okay. And then 3, 4, and 5, I asked you just to do one of them. I'm going to go through each of them if I think we'll have time. So let's look at these. All right, question 3. Hydrogen gas burns in air to create liquid water at standard conditions. So burning is combustion, right? So here I have H2 gas plus O2 is going to yield H2O. And I can balance this. I'm going to balance it with a half right here. Of course, you could have balanced it with a 2 and a 2 if you had wanted to. Calculate the standard enthalpy change for this reaction, given that the standard enthalpy of formation for liquid water is this value. Enthalpy change for this reaction, given that the heat of formation for liquid water is, and this is liquid water, they're telling me I created liquid water here. So that's going to be delta H equals heats of formation of products minus heats of formation of reactants, because I've been given the heat of formation of water. However, I know that the heat of formation of my reactants are both 0 because those are in their standard state. So I'm trying to find the enthalpy change for this reaction, delta H. Well, it's just going to be equal to the heat of formation of my product, which is negative 285.8 kilojoules per mole. So that's just my answer, negative 285.8 kilojoules per mole. Just like that. Now, I suppose that if you had balanced your equation differently, if you had balanced it using a 2 right here and a 1 right here and a 2 right here, then you, in order to find the delta H for this reaction, you would have multiplied this number by 2 and then subtracted 0 away from it. But you would have had to have just divided it by 2 again to get the standard enthalpy change for the reaction. That's always per mole of a substance. I guess if you had reported it per mole of oxygen, then you would have been able to keep that double number. So I'll have to look at that. But really, this should be the answer. If you got an answer twice that amount, it's going to depend on how you reported it. In other words, if I did balance it like this, then my equation would become delta H equals heats of formation of the products minus heats of formation of my reactants is still 0. Heats of formation of my products is going to be twice this value. And so I would have gotten 2 times that number. Let me see what that is. 2 times negative 285.8, negative 571.6 kilojoules. But then you would have had to have said per mole of O2 or something like that, because that is the thing that has a 1 in front of it. And that's kind of a weird way of writing it. I'll give you points for that if you did that. But really, whenever we're asked for standard, we want to put it in terms of per mole of like everything else. And so really the best way to balance this would be to have a 1 right here, a 1/2 right here, and a 1 right here. I'll have to look at those. Okay, so let me erase that mess and remind myself that this answer is 285.8 kilojoules per mole of water formed. Here's the reaction I'm looking at. Okay, calculate the amount of heat that's released when 10 grams of hydrogen gas is combusted to create liquid water at standard conditions. So I know now, based on my answer to part A, how many kilojoules of energy are released when 1 mole of water is formed from 1 mole of hydrogen gas being combusted. But now I want to know how much heat energy is released when just 10 grams of hydrogen gas is combusted. So I'm going to start like this. I'm going to say, okay, I know that 285.8 kilojoules of energy are released per 1 mole of H2. That's how many kilojoules per mole are released per 1 mole of H2. but I don't have 1 mole of H2. I have 10 grams of H2 going on the bottom. And then I need to put the molar mass of H2 on the top, which is 2.02 grams. Sorry, this is hard for you guys to see. And that's going to give me my answer. That's going to give me, wait a second. I did not do that conversion correct, did I? Whoops. Okay, let me start that over. I'm so sorry. H2 plus 1/2 O2 yields H2O. Okay, I know that negative 285.8 kilojoules are released per 1 mole of H2. I know that 1 mole of H2 has a mass of 2.02 grams, and I know that I'm actually combusting 10 grams of hydrogen gas of H2. So doing a conversion like this is the only way to get grams to cancel out, moles to cancel out, and just be left with some amount of energy. So we perform that calculation. And I got an answer of 14.9 kilojoules of energy are released whenever 10 grams of hydrogen gas are combusted. I guess if we're worried about sig figs, I should really only have 3 sig figs, so negative 1410. Okay, then part C. This is going to be a Hess's law type question. So my reaction right now is the combustion of hydrogen gas plus 1/2 oxygen gas yields liquid water. And they tell me that that whenever this reaction occurs, but instead releasing gaseous water, that I want to know what the enthalpy change for that reaction is, what the delta H of that reaction is. And they tell me that the enthalpy change for vaporizing liquid water is 44 kilojoules per mole. So I know the delta H for this process is negative 285.8 because, again, that was coming from part A. And now they're telling me that when I get H2O as a liquid vaporizing into a gas, that delta H is 44 kilojoules per mole. So it's like, these are my puzzle pieces, and this is what I'm trying to find. This is the picture on the puzzle box. So I've got to combine these somehow to get this. So what I need is 2 moles of gaseous hydrogen as a reactant. So it looks like I'm going to have to multiply this whole thing by 2. So I'm going to have to balance it this way now. 2, 1, 2, multiply this by 2. To get me negative 571.6. And I need to cancel out that liquid and get a gas, right? And I need 2 moles of a gas. So it looks like I'm going to have to multiply this one by 2 as well, and multiply that delta H by 2 to get 88. And when I add these together, you can see that my liquid water will cancel out, and I'll have gaseous, 2 moles of a gaseous water as a product. So there's my reactant, my product. That is the picture on the puzzle box I'm trying to make. So I've manipulated my puzzle pieces correctly. All I have to do now to find the enthalpy change for this is add these together. And it looks like the answer is going to be negative 483.6 kilojoules. All right. Okay, we've got about 10 minutes left, so hopefully we can make it through these last two questions. Okay. stop. Okay. Liquid hydrazine into H4 combusts plus O2 to create nitrogen gas and water vapor. The standard enthalpy change for this reaction is negative 534 kilojoules per mole. All right, so I should maybe try to think about balancing this. So let's see. I just need to put a 2 right there. And it is balanced. Predict the sign of entropy for this reaction. Well, this is a liquid and this is a gas. And after it combusts, I get even more gas. So of course the entropy is going to be positive. The entropy change is going to be positive. In other words, my system is becoming more chaotic. I have 1 mole of a liquid, 1 mole of a gas, and I go to getting 3 moles of gases. So even if I didn't balance the equation, I could figure that out, right? Of course, I'm going to have more gas on the product side. So my process ends up increasing the disorder. Is the following statement true or false? The large negative delta H for the combustion results from the large release of energy that occurs when the strong bonds of the reactants are broken. That is false. And if anyone wrote true, then ooh, I'm going to be very sad. That, of course, is false because what happens, energetically speaking, when we break reactant bonds? We have to put energy in. So what is making it so exothermic has nothing to do with the reactants, but everything to do with the products. Is that these product bonds are quite strong. They have large bond energies. So a lot of energy was released when those were formed. So part B is very, very false. Make sure you justify your answer that when you break reactant bonds, energy has to go in, okay? All right, question 5. The gas inside a hot air balloon is allowed to cool in preparations for landing. The volume of a gas shrinks under that constant pressure, while that much heat energy flows in. Find the energy change for this process. So I know that energy change can occur when 2 things happen, when there's heat added and when there's work. And remember that work for a gas is equal to pressure times change in volume. And my volume has gone down. So if this is my balloon and the volume has shrunk, I know that I can think about it as if the surroundings are doing work on the balloon to do that. I know that the balloon shrunk because its volume decreased. So the surroundings are doing work on the balloon. So my work term needs to be positive then. So even though that the change in volume is a negative change, the volume went down, the surroundings are doing work to like press the balloon in. So my balloon is gaining energy from work, but then it's losing energy from heat leaving. So my final equation is going to be negative 1.42 times 10 to the 7th. That is going to get me the energy lost due to heat. And then I'm going to add to that the energy that gets gained whenever the work is done on the balloon. The surroundings are compressing it. And that's going to be the pressure of 0.89 times whatever the volume change was. And I'm going to treat that volume change as a positive number, so I end up getting positive work, right? So it looks like the volume change, 3.42 minus 2.89 is 5.3 times 10 to this 10 to the 7th. Anyway, the key to this question was making sure your signs were correct. The heat energy is flowing out. It's losing heat energy to the surroundings. and the surroundings are doing work on the balloon to compress it, to squish it down. They're applying a force over a distance to compress the balloon. So my my work term needs to be a positive number. Yeah, and then whatever the math is for that, I don't want to do it right now because we're almost out of time. Hopefully this was somewhat helpful for you. Hopefully this helps wrap up Unit 5 for you. Does anyone have any questions before we go? You guys feeling okay about everything? If you all don't have any questions, I guess we are good to go. So listen, at this point, you should have watched, how am I going to grade these tests? So I'm just going to grade the exam that you turned into me last week, and I'm going to apply a very, very nice curve to that exam. And then I'm going to give you points for showing up today. And all those points will contribute to last quarter's grade. Your grades from last quarter basically end with this exam and this meeting that we're having right now. And I'm going to get those grades in hopefully sometime today or tomorrow morning, and your grades will be finalized. And this exam will get, oh yes, the lab report. Shoot, I have to grade that. Thank you. Yes, the lab report will also go into last quarter, and the work that you did for Unit 5 as well. So yeah. As far as Unit 6, kinetics, you guys should be taking notes over those 2 videos, uploading pictures of your notes, and you really need to start working on the packet. I uploaded a kinetics work packet and some other resources for you on my Haiku website. So someone asked where I got like the cheat sheet that I showed in the video. That is uploaded on my Haiku website. So please make sure you go to the My Haiku website as well. It's linked somewhere on the Google Classroom, so you can find all the stuff for the kinetics unit. And you need to start working on some problems from the kinetics packets, because tomorrow we're going to have another Zoom meeting, and that meeting will only go well. It will only work if you guys have seen the 2 kinetics videos, taken notes, and if you've started to try to work to solve some of the problems from those packets. You don't have the knowledge to solve everything from the packets, but you have knowledge to solve something from the packets. So you need to start working on those, okay? Because tomorrow I'm going to take your questions over the videos that you've seen. We're going to be working some problems together, so that you guys have a good start on Unit 6. And then it will be spring break, okay? All right, guys, thank you so much for your time. Y'all hang in there, wash y'all's hands, don't leave your dang houses, stay safe, stay healthy, and I will see you all tomorrow. Please let me know if you have any questions or if you need anything at all, okay? And I'll see y'all later.